So let's introduce the next big concept for the course, and that's momentum. Now, for starters, as long as we're dealing with our sort of point mass model for objects, talking about the momentum and talking about the linear momentum, those are the same things. Um, when we start to talk about extended objects, then we'll see that there's sort of two different ways we can characterize the momentum. But for the moment, let's just worry about the linear momentum, and we'll tend to just refer to that as the momentum. So what is this? Well, one way to think about the momentum is that it's a measure of an object's quantity of motion. And your initial reaction to that might be, well, wait a second, that definition doesn't give me any more insight than just talking about the momentum itself. I don't know what quantity of motion means. And this is a little bit by design. Again, this is another one of those concepts that in some sense is so fundamental that we don't have other more basic words to use to define it. So we saw that same thing with energy, where we said we don't have a really good definition for energy in words to describe what energy is because it's so fundamental an idea. Momentum works the same way. It's so fundamental an idea, we don't have a really good definition in words. So what did we do with energy to sort of hide our ignorance? Well, largely we used an equation. We're going to do the same thing here. We're going to say, hey, there's an equation that I can use to calculate the momentum of an object. It happens to be that P, that's the letter we're going to use for the momentum, is equal to m, the mass of the object, times the object's velocity. So momentum is equal to mass times velocity. So what does this equation tell me? Well, the first thing it tells me is that momentum is a vector quantity. So again, I recognize that I have a vector equation. Like any vector equation, I need to break it up into however many component equations I have that define what's going on in my space. Again, for this class, what we'll tend to do is work a lot of problems that are in two dimensions. So we'll often break up the momentum equation into two components, x component and y component. Again, it's a momentum, or it's a vector equation. And because I know the mass is always positive, that means that the momentum vector and the velocity vector always point in the same direction, right? So this is actually a really useful idea, because what it means is that even though I may not have a great definition for what the momentum is, I do have a really good way for figuring out which direction it points in. If you know the direction the object is moving, and therefore you know the direction of the velocity vector, the momentum vector has to point the same way. So that tells me about the direction. What about the magnitude? Well, the magnitude of the momentum depends on both how massive the object is, that's the m part, and how fast that it's moving. So the magnitude of the velocity vector is just another way of talking about the speed. So if you want the magnitude of the momentum, that's just going to be the mass of the object times its speed. And then again, I can use this equation to figure out what the units are for momentum. So the units of momentum have got to be equal to the units of mass times the units of speed. Well, units of mass are kilogram, units of speed are meters per second. So I get that the units of momentum are going to be kilogram meters per second. Now, as fundamental a quantity as momentum is, oddly enough, we haven't given it another name for its unit. So we haven't done like what we did with the Newton or the Joule or anything else where we say, hey, let's give it another name for that unit. We tend to just keep the units of momentum in base units. So we're just going to use kilogram meters per second for the units of momentum. All right, so why is momentum important? Well, part of what that quantity of motion was trying to tell us, right? So again, that's a phrase that Newton himself came up with. And even though he used it in a slightly different way, the insight that it provides is still pretty much the same, in the sense that it's saying that thinking about the purely kinematic thing, the velocity by itself, isn't really enough if you want to keep track of an object's motion correctly. So this takes us from kinematics and places us back into dynamics. So including that m, so the quantity that you really care about keeping track of, if you want to figure out how an object is moving and why it's moving that way, is not just the velocity, but it's this quantity mass times velocity. So what we're going to do, if we want to keep track of how the momentum changes, well, that's just a change in momentum vector. That's final momentum minus initial momentum. So notice what we'll end up doing is a vector subtraction problem to keep track of how the momentum is changing. So let's consider that we've got an ant walking around on a piece of paper, and initially the ant's down here in the bottom left-hand corner of the paper walking up the page. And we look back some time later, and the ant's now up in the upper right-hand corner of the paper walking off the page to the right. So again, I know the initial velocity of the ant pointed up, the final velocity of the ant pointed to the right, which means that I know the direction of the initial and final momentum vectors. And so I can draw them out. And so here, if the initial velocity of the ant points up, then the ant's initial momentum must also point up. If the final velocity of the ant points to the right, then the ant's final momentum must also point to the right. And then working the vector subtraction problem, final minus initial momentum, says I simply need to draw in the vector that connects from the tip of the initial momentum to the tip of the final momentum. So here's delta p, right? Here's the change in momentum vector. So if I want to calculate this out, well, again, I'm just going to break this up into components. So again, doing a vector subtraction problem, we're comfortable with that process at this point. So I know that I'm going to have x and y components for delta p, and then I need to figure out the x and y components for both my initial and final momentum vectors. And again, you'll notice that I've put them into this table where I've got final on top of initial, just to help me keep things in the right order for when I do my vector subtraction. So in terms of this, so I can take my table and set up these two equations. And so in general, the x component of the change of momentum is nothing more than the x component of the final momentum minus the x component of the initial momentum. And the y component of the change in momentum is nothing more than the y component of the final momentum minus the y component of the initial momentum. So here's sort of in general how we define the x and y components of the change in momentum. In this particular example, since the final momentum points in positive x, therefore the y component 0, and the initial momentum points in positive y, therefore the x component 0. I can plug that in. Here I've got, and so what I end up with is the x component of the change in momentum for my ant walking around on the sheet of paper is the final momentum minus 0, which is just going to be the mass times the final speed. And the y component of the change in momentum, 0 minus the initial momentum, and so that's going to be negative mass times the initial speed of the ant. And again, just like with anything else, if I know the x and y components of a vector, here it happens to be the change in momentum vector, but if I know the x and y components of a vector, I can Pythagorize those to get the magnitude. So x component squared plus y component squared, take the square root. I can use inverse tangent of those of the y component over the x component to get an angle relative to the x-axis for the direction of the change in momentum.